Hello. Um, Today, in today's video, we're going to go through some worked examples of how we formulate mathematical models from various sorts of um, somewhat simplified real-world-like problems. We're going to cover a range of different problem types. Um, and for each of them, we're going to go through the whole process, presenting a problem that is uh, given in mostly written English, although a fair bit of numbers involved in presenting the problem. Develop the model, formulate a mathematical model, think about what we're trying to find, um, go through the execution or attempt to go through the execution of finding the result, um, and then take that answer and move it back into the original problem. So let's get started. The first problem we're going to take a look at is example of an industrial production problem. We can find examples of this in the Tucker textbook, but these are sort of very ubiquitous, sort of very commonly phrased types of problems for trying to understand how we balance inputs and outputs, or sources and products in industrial production. So the question is given up on the screen, and you can read it, but I'll sort of go through it also. We have an oil company that has a number of different types of refinery, type 1, 2, and 3, and each of those different types of refinery produces different outputs based on the crude oil that is input. The first produces 15 gallons of gasoline, 5 gallons of kerosene, which is jet fuel, 10 gallons of diesel, 5 gallons of fuel oil, and 5 gallons of asphalt per barrel input crude. Type 2 produces 20 gallons of gasoline, 10 gallons of kerosene, 10 gallons of diesel, but doesn't produce any fuel oil or asphalt. The third type produces 10 gallons of gasoline, 5 gallons of kerosene, 5 gallons of diesel, 10 gallons of heavy fuel oil, and 5 gallons of asphalt. So type 1 is kind of a balanced production of all types. Type 2 is weighted to the lighter products, and type 3 is sort of slightly overrepresented in the higher weight products. And the question we're interested in is how many barrels of crude oil need to be processed by each class of refinery if the goal is to produce 80 million gallons of gasoline, 30 million gallons of kerosene, 40 million gallons of diesel, 45 of fuel oil, and 30 of asphalt. So how do we take this problem, phrase it into a mathematical model, and then work with that model to get the desired answer? Remember that we're going to sort of try to do this systematically, having kind of a step-by-step process for how we think about dealing with this kind of problem. First of all, we need to define variables. Always the first step in formulating a model should be thinking about what are the variables in the problem, define those so that we can then think about writing out equations that represent the information given. In most cases, the variables are going to be the unknown parts of the problem, although in some cases there will be unknowns that we represent as symbolic constants instead, or as well. In this case, really the only unknowns are the numbers of barrels of crude oil processed by each class of refinery. So we define our variables to be those unknowns. The symbols I've chosen to use are x1, x2, and x3, each representing the number of barrels in millions, because we don't want to carry a whole bunch of extra zeros around, processed by each type of refinery. So x1 is the number processed by type 1, x2 is the number processed by type 2 refineries, x3 the number processed by type 3. Okay, once we have our variables in place, we can think about trying to express the information present in the problem in terms of a number of equations that capture all of the information. So how do we do this for this particular problem? Well, if we think about what we have three different types of refinery. We've already defined a variable associated with how much is processed by those. We also have a number of different types of output product: gasoline, kerosene, diesel, fuel oil, and asphalt. Each one of those outputs can be used to give one equation, where each equation gives the total amount produced as a function of the number of barrels processed by each type of refinery. On the left-hand side, we will put the actual production, and on the right-hand side, we'll put the target production value. So what would this look like? For gasoline, the actual amount produced will be 15 gallons of gasoline multiplied by however many barrels of crude were refined, so 15 times x1, plus 20 gallons of for every barrel of type 2, plus 20 x2, plus 10 gallons for every barrel of processed by type 3. So essentially taking one value, 15, 20, and 10 for each of these sort of sentences, descriptions of how much is produced by each type refinery, gives us the left-hand side of our first equation. This is the actual amount of gasoline produced, and what we want to produce is 80 million. So what we would like is this side to equal 80. This is our goal. We can do the same thing for each of the additional outputs. For kerosene, we have 5 from type 1, 10 from type 2, and 5 from type 3, giving us 5x1 plus 10x2 plus 5x3. And we have a target of 30 million gallons. And let me change this to make it a little bit easier to see here. For diesel, we have, for type 1, 10 gallons per barrel. For type 2, 10 gallons per barrel. And for type 3, 5 gallons per barrel. 10x1 plus 10x2 plus 5x3. Our target is 40. Doing the same for the last two, fuel oil, we have 5, no for produced by type 1, nothing produced by type 2, and 10 produced by type 3, with a target of 45. That gives us this equation. And for asphalt, we have 5 produced by type 1, nothing produced by type 2, 5 produced by type 3, and a target of 30. So 5 equations for each of the 5 output products, where every equation has the same form of constant times the the first variable, a constant of the second variable, and so on. And our targets are on the right-hand side. So in summary, this is now our model that we've written down, where xi is the number of barrels processed by each type refinery, and our 5 equations for our 5 outputs. Now is the time to think about what are we trying to find. What we would really like to find are values of x1, x2, and x3. That is the number of barrels processed by each refinery that simultaneously satisfy each equation. If we could do that, then we would be able to perfectly satisfy the targets. How do we go about doing this? Well, it's not immediately apparent the easiest way to do so. Maybe we could do some substitutions. There are a couple of equations that only have 2 variables. Maybe we could rearrange those to express one variable in terms of the other, and then substitute it in, and then do the same for the next step. We could try that approach, and let's see how that goes. Right? Let's see how we figure out how we might do this. And I want to emphasize there are lots of strategies that you could take to try to solve this system. This is simply one way that we might get an answer. So let's take a look at these last 2 equations. As we said, these both only have 2 variables in them because they have a 0 coefficient for the middle one. This makes it a nice place to start. One thing that we might try to do is let's try to even reduce these variables even further. One way we can do that is by subtracting the equations. So let's take equation 4 and 5 and subtract the second one from the first. Equation 4 subtracting equation 5 makes the first piece disappear because they have the same coefficient. So 5x1 minus 5x1 is of course 0. 0x2 minus 0x2 is also 0, leaving us only 10x3 minus 5x3, which is 5x3 on the left, and 15 minus 30 is 15 on the right-hand side. This tells us that x3 must be 3. We might also notice that actually the second 2 equations have the same values for the same coefficients for x2 and x3. The same strategy of subtracting equations would make both of those pieces disappear. So the second equation, the third equation minus the second equation, just doing this just so we avoid negative signs, gives us 10x1 minus 5x1, 5x1, 0, and 0 equals 40 minus 30, which is 10. So x1, of course, has to be 2. Now we've used equations 4 and 5. We've used equations 3 and 2. How about we now use equation 1 and plug those answers for x1 and x3 in and find x2. So plugging in the first equation of 15x1 plus 20x2 plus 10x3 with x1 equals 2 and x3 equals 3 gives us 15 times 2 is 30 plus 20x2, we still don't know x2, plus 10 times 3 is 30 equals 80. Right? 30 plus 30 is of course 60, so this gives us 20 x2 equals 20, or x2 equals 1. Looks like we have an answer. x1 equals 2, x2 equals 1, and x3 equals 3. Very important with these kinds of systems, it is not sufficient to get something that looks like an answer and then stops. We have not actually used all of the information in this system to get this answer, because in subtracting out these equations, we've lost some of the information, right? Really, we've only used 3 pieces of information, 2 differences and 1 equation by itself, but we have 5 equations. We verify these by plugging in these answers into all of the equations. We've already done it for 1. We know that works. And double checking that it works for all of our answers. What happens when we do that? When we plug in x1 equals 2, x2 equals 1, x3 equals 3 to these 5 equations, we actually find that while the first equation is, of course, is true, the second equation, which gives 5 times 2 plus 10 times 1 plus 5 times 3, or 10 plus 10 plus 15, doesn't equal 30. The left-hand side is 35. The right-hand side is 30. 35 is, of course, greater than 30. We have an error of positive 5 on our actual production and our target. If we plug these same values into the third equation, we end up with 45 on the left-hand side, 40 for the target. Again, false, an error of plus 5. The last 2 equations also are not perfectly satisfied. We have 10 plus 30, which is 40, is less than the target of 45, and 10 plus 15, which is 25, is less than the target of 30. So we have errors of plus or minus 5 in 4 out of the 5 equations. We say the solution is inconsistent. We didn't do anything wrong. We worked through the problem. Every step that we took gave us a sort of correct answer based on what we had. But after doing so, we end up with this sort of set of inconsistent answers. When this happens, the reason for it is that this system of equations doesn't actually have an exact solution. There is no choice of production values for the 3 refineries that will perfectly match all 5 targets. The production values aren't that far off. They're within 5 of the target. And in terms of a percent error, the largest percent error, since all of the absolute error is the same, would be that divided by the smallest target, which is 30, or about 16, 17%. Maybe we can do better. How can we do better? One approach might be to try to adjust our answer. We got an answer that's close but not perfect. Can we find a way to make it a bit better? How we do this might not be perfectly clear. We might take a look and we say that these 2 values are too small, while these 2 values are too high. And the difference between these 2 and these 2 is that there's a fairly significant coefficient in front of x2 for the second and third equation, and 0 in front of this. So perhaps if we were to decrease x2 a little bit, that would decrease these numbers. We'd also decrease this one a little bit without affecting these. If we also increased x3, x3 has the smallest impact on these. We've decreased x2. Increasing x3 might offset that a little bit, but increasing x3 would bring these numbers up a little bit and also might help sort of balance off how these sort of changes to the first equation happen. By how much? The only way really to sort of get a sense is to go ahead and try something. If we sorry, if we decrease x2 to a half from 1 and increase x3 to 3.5, so move one down by 0.5 and one up by 0.5, and then plug those numbers in, what we end up with is still four false answers. The first equation ends up now giving us 75 on the left-hand side and 80 on the right, an error of 5 again. The second equation has its error reduced. The left-hand side now gives us 32.5 compared to 30, so an error of 2.5. The third equation gives us also an error of 2.5. This change actually makes the fourth equation now perfectly true and makes the fifth equation off by negative 0.5. So actually, where we had the 4 errors of plus or minus 5, we've reduced those errors by at least a factor of 2, but we've introduced a new error into the first equation. However, the maximum percent error of this is significantly lower. The largest percent error is 2.5 over 30, which is actually a lower percent error than the 5 over 80, which is about 8.3%. We've actually decreased the error by 50% in a percentage sense. That's a significant improvement. We're below 10% error. Maybe we could do better by finding a different adjustment, but to do so is a very tedious process. Even if we're able to sort of make refinement and refinement and refinement, this guess and test and make an adjustment and test again is a very imperfect way of solving the problem. In particular, we get no assessment of how well we can do. We never know really whether another guess might have been able to do a little bit better. With the tools we have right now, there's not really much more we can do. We will be finding throughout the class that we have robust ways to solve this kind of problem and definitively say, at least with some measure of what it means to be best, what the best possible answer in this kind of situation is. Always important to remember, after we've dealt with the math part of the problem, we need to come back to the original problem and give our answer in terms of the problem we were posed. The way we do this in this is to note, first of all, there is no way to perfectly match these targets, but if we were to process 2 million gallons of crude through type 1 refineries, 500,000 with type 2, and 3.5 through type 3, we would be able to get productions within 10% of each of the targets. That's a description of our answer in the context of the original problem.